Now, so we spoke so far about corporate devices, non-corporate devices, and guests. But there's also something else which we need to be aware of, the mobile device management. So now, BIOD enrollment can be achieved either via ICE or via a mobile device management platform. That's what MDM means. And MDM has changed the name in the last, I think, 2 years or so. It became Enterprise Mobility Management because the EAM can not only control mobile devices, because initially it was named Mobile Device Management because it was a platform aimed to manage the mobile devices. But now MDM has evolved. It allows managing also laptops and computers, which that's why the name changed to Enterprise Mobility Management, because we manage all enterprise mobile assets like phones, smartphones, tablets, and computer laptops as well. Now, of course, if BIOD is supported by both MDM and ICE, then why would you choose MDM against ICE? Because MDM supports additional features for mobile devices and also for enterprise assets, but it's most importantly for mobile devices. So for enterprise assets, ICE is more feature rich than MDM, except as long as those assets are not mobile devices. But for mobile devices like smartphones and tablets, then an MDM or EMM technology or technology application is more feature rich than ICE is. So MDM allows to perform posture assessment on the mobile devices. Like what this means is that, for example, as we said before, that we want ICE to give network access to the users based on the health state of the system. We're going to see in a couple how ICE can identify the health state of a system as long as the system is a computer device like a desktop or a laptop. But ICE cannot detect the health of a system if the system is a mobile device. So that's the main advantage of using MDM. Because through MDM we can detect if the device was jailbreaked. If the device uses or doesn't use a PIN code, we can of course enforce the usage of a PIN code. If that mobile device has encryption turned on or not. What is the software installed on that mobile device? And based on all of those aspects that can be controlled via MDM, then what this means is that, for example, MDM is gonna communicate with ICE, because in the end ICE grants network access to the network to mobile devices, not the MDM platform. So if we look in here at a diagram, let's assume that this is a mobile device. This one is a mobile device. So we're gonna have the MDM platform in here, which MDM platform is going to be used to manage those mobile devices. So MDM is going to push some configuration profiles to the devices, like an email configuration profile for the enterprise email, a VPN configuration profile for the AnyConnect client, a Wi-Fi connection profile, because you don't want users' mobile devices when they connect to the network to ask around, or users are not in general capable of configuring by themselves the Wi-Fi connection, the VPN connection, the email configuration, and it's not scalable to call in all of those users to a help desk support. So those people are going to configure those devices, Wi-Fi, VPN, and email clients. So rather off the MDM technology, the MDM, let's say software, is gonna push over to those devices all of those profiles: the VPN profile, the .1x profile, the email profile, the Wi-Fi profile, and so on. But in the end, so that's only to manage the device and perform some restrictions on the device. But in the end, when that mobile device wants access in the network, he's gonna get authenticated still via ICE. So ICE controls in the end who can access the network and how. So for this reason, what we want is we're gonna configure ICE and MDM to intercommunicate, to exchange some information back and forth. Because what we want is that, for example, let's say that our company policy, MDM wise, states that devices should not be jailbreaked. Because if a device is jailbreaked, then a lot of the built-in security features of that device are gone. So that's a security issue. Also, our policy states that the mobile devices should not have specific applications installed, like for example application A installed, because we know that that application may contain malware. But the challenge is that if the user's device is jailbreaked, or if that user's device has that application enabled, ICE cannot know that. So that's why ICE is going to communicate with MDM, because if this device in here is not conform to the company policies, it's jailbreaked, then MDM is going to know about that. And MDM is going to tell ICE, dear ICE, we have this user, this mobile endpoint, which is jailbreaked. It's not doesn't conform with the security policies of our company. So what this means now ICE knows about the health state of that mobile device. So when the user wants to connect to the network with that mobile device, ICE is going to say, no, I don't let you in because your device is not confirmed with our policies. Or ICE is going to say, okay, I let you and I give you network access, but restricted, because your device is not 100% conform with our security policies. So for that reason, ICE integrates with MDM to exchange back and forth information, so that we want to allow network access of mobile devices in the network, also by being aware and based on the health state and on the compliance state of that device with our corporate policies. So that's why we would integrate ICE with the MDM platform. Now the authorization part, so once the device has been authenticated, authorization is likewise done based on the context. So based on who's the user, when it got connected, how, like VPN, Wi-Fi, wired, from where, and what, then we are going to be able to, we're going to assign the user different authorizations. So the same user from the same device may get a different authorization based if it's coming from a VPN connection or from a Wi-Fi connection, or if it's coming at 3 AM in the morning to be connected to the network. The commonly used authorizations that ICE is going to push over to the authenticator to control network access are going to be VLAN assignment. So we're going to put that user in a specific VLAN, and ACL assignment to restrict what traffic can that user send in the network. Let's say also commonly used but not widely deployed, because it's kind of like a new technology, sort of. Actually, it's not a new technology, but also ICE can authorize network access by using TrustSec. With TrustSec means trusted security, and we're going to speak later on about that. It's built. It has two main components: SGT and MACsec. And the system health state is determined via partial assessment for laptops and for computer laptops and desktops, because ICE would want to give network access also based on the health state of that system, and ICE is going to be aware of the health state of the system. If the system is a laptop or a computer desktop, is going to know that via partial assessment. If the system is a mobile device, is going to know the health state of that mobile device by communicating with the MDM platform. So partial assessment means that on the laptops and computer desktops, we're going to have a client running on that end system which verifies compliance with the enterprise policies. Like as I stated, is the firewall turned on? Is the antivirus engine installed and up to date? Is your operating system up to date? Or is the client infected, for example? Now let's speak about TrustSec. So TrustSec stands for Trusted Security, which means we want to, this is a framework developed by Cisco, which means we're going to give network access to users and devices in a trusted way. And TrustSec has two main components: SGT, which stands from Security Group Tags, and MACsec, which is a standard 802.1 AE. Now, SGT is nothing else but a 16-bit value security tag or label attached to IP packets. And the label can be imposed either in the layer 2 header or layer 3 header, or of course both of them. You can look at this tag like the VLAN tag, but while the VLAN tag has a scope of separating the broadcast domains, the SG tag has not a scope. The scope is to identify the user in the network and control what access does that user have. So you can look at like a regular label which identifies that user in that device in a specific context, like from where did it connect, when did it connect, and how did it connect. And based on that SGT value, we're gonna grant different. We're gonna control what a user can do in the network. While MACsec is nothing else but hop by hop line rate layer 2 encryption. Is layer 2, just the name states. MACsec stands for MAC security, which means we're gonna protect and secure the layer 2 payload, which means nothing else but the layer 2 header is visible in clear text. And because it's hop by hop, can be host to switch or switch to switch. We're gonna see in a couple a bit more about both of them. Now the SGT architecture, let's take it one by one. Let's speak about SGT. So the scope of SGT, why did we invent this let's say technology, is for scalable firewall rules. So instead of restricting users access via access lists, we're going to restrict user access via SGT values. So why do we need this? For a very simple reason. Like imagine nowadays one user with one device can be connected via VPN, so it's going to get assigned one IP address, can be connected via wired but from multiple locations, which is going to have 10 or 15 IP addresses assigned depending on the location it connects to, via wireless, again from different locations of the company. Likewise, it's going to get assigned a lot of IP addresses. So assuming we want to give to that user the same network access regardless of the connection point, it's not scalable to perform firewall rules and put in there for the same user 20 or 50 rules just because that user is going to get assigned different IP addresses. So it's not scalable. Because again, if that user gets different IP addresses assigned based on the connection type and connection point, and we want to give to that user the same access type to the network, it means that somewhere when we have a firewall in the network, we're going to have to configure for the same user 20, 50, 60 plus rules based on how many possible IP addresses that user can get assigned. So like if we look at the TrustSec overview in here, so without SGT, then when this user connects, he's going to have a specific IP address assigned. And then we have to configure somewhere in the network, like DC firewall, to restrict what traffic can go from the enterprise to the data center side. And as I stated, imagine that this user in here, this user can get multiple IP addresses assigned based on a connection point and type, which means that for the same user, I'm going to have to configure on that firewall a lot of rules, and that's not scalable. Not only from the hardware point of view scalability, but also from the management of configuration point of view. So the outcome is that we want to control network access of the users no longer based on IP addresses, but based on the context of that user. So the context is going to in the end mean the SGT tag value assigned to that user once it got authenticated in the network. Now for SGT to work, we have three main components. We have the classification part, where it means that we have to assign an SGT value to a specific user or specific device. The transport part, which means in order to be able to configure firewall rules based on SGT values, it means that that SGT value has to be transported across the network. So impose the label, that SGT value, and preserve the label in the network as traffic flows through the network. And the third part is going to be, of course, enforcement, meaning we're going to go in our network in specific places and configure firewall rules based on SGT values, not based on IP addresses or usernames. Now, SGT classification can be done statically or dynamically. Now, statically is usually done for servers because servers don't perform .1x authentication. So usually you don't authenticate servers connected to the network because they are in the data center. So for sure, you have other ways of making sure who can connect anything in the data center. It's other security measures in there. And dynamic classification, so dynamic SGT assignment is going to be done usually for users or devices which are going to be connected in the campus or via VPN or from remote branches. And dynamic classification, so assigning SGT values to users or devices, is going to be done by ICE. So what happens is that when a user gets authenticated or device gets authenticated, based on the context of that user, ICE is going to assign SGT value of 9 or of 19 or of 25. So based on that couple of who's the user, what kind of device, from where did it connect, when did it connect, and how did it connect, I'm going to assign to the same user maybe different SGT values. So that was the classification part. And let me see if we have in here something that I can show you in the Cisco's documentation. I want to show you in the end another document. So that was the classification part. So again, tags can be, traffic can be classified, and tag assignment can be done in two-way, static or dynamic, and we spoke about both of them. Then we have to speak about transporting and imposing that tag to users' packets. And we have what is called inline SGT transport, which what this means is that the authenticator is going to impose the SGT to packets from authenticated users' devices. And the transit network will just preserve the SGT tag value. But for the authenticator to perform this, so once ICE has authenticated the user, then all traffic coming from that user, from the VPN or from the Wi-Fi or from the wireless, the authenticator, which is going to be the VPN gateway or the switch the user got connected to or the wireless LAN controller, is those authenticators receive traffic from the user. They're going to impose that label on the user's traffic and send that traffic labeled with the SGT tag value in the network. But for this to work, the authenticator requires both hardware and software capabilities. So for that reason, not all devices have this capability, which means we have a new protocol which is called Security Tag Exchange Protocol, SXP, which is used to fix this problem when the authenticator cannot impose the tag value received from ICE. So SXP is going to be a control plane protocol based on TCP, which is going to signal is going to signal to other devices which are capable for inline SGT transport. Is going to signal to other devices the SGT to IP mapping as received from Cisco ICE. And that's going to be a point-to-point connection of type TCP between what I call the SXP speaker and the SXP listener. If we look in here in a trusted documentation of Cisco, Then how this works is as follows. There we go. So let's suppose that we have, so this is the supplicant, this is the authenticator because the user is connected to a switch, and let's suppose that this is going to be the ICE server in here, the authentication server. So what this means is that when user connects to the network, the switch is gonna send the credentials to ICE for validation, and what ICE is gonna do is gonna return back to the switch a OK message saying user authenticated. Is gonna return also an SGT value, telling the switch assign this tag value of 10 to all packets received from that user. So then when the user sends IP traffic in the network, this being a inline capable switch, when the switch forwards the packets further in the network, is going to impose or attach to the IP packet the label as received from ICE. In this case, they use a label of 100. And as you can see, each network device in transit, if it's capable of inline SGT tagging, as it forwards the packets further in the network, is going to preserve that value attached to the IP packet. Now we have another use case in here of another user connection, but the switch that the user is connected to, that it's an older model, doesn't have inline capability, doesn't have the capability to enforce the tag inline. So what's going to happen is that again, the user connected to the network, it sends its credentials to the authenticator. The authenticator has sent the credentials further to ICE for being authenticated. ICE said, okay, user got authenticated, and ICE said, assign a label of 100 to that user's traffic. But because that authenticator is not inline capable, what the switch does through this SXP connection to another device, where this device is inline capable, it can impose label to IP packets. Then the switch is going to be, this is going to be the SXP listener, speaker, the SXP speaker, and this is going to be the SXP listener. So the switch, the authenticator, the SXP speaker, is going to tell to the SXP listener, to this SXP session, the IP to SGT mapping for this user. So now what happens is that when this user sends IP traffic in a network, the switch is going to forward it as it is because it cannot impose an SGT tag value. But now when this device receives the IP traffic, because this device is SGT capable inline, and because it has received from the switch the IP to SGT mappings via the SXP session, now when this switch receives the traffic and sends it further in the network, it is going to impose the SGT value as he learned it from the authenticator in there. So that's the use case of the SXP protocol. So far we spoke about how the SGT value gets assigned statically or dynamically, then how the SGT value gets imposed to the IP packets. The last step is going to be exactly the scope of SGT. Then okay, how can we build firewall rules to control IP traffic in a network based on the SGT values? So the SGT enforcement. So now we're going to build firewall rules in the network to control IP traffic in the network based on the SGT values. We have two options for that: the security group access list and security group firewall functions. Now the SGACL, it means that we're going to define on ICE, so still centralized, a matrix of traffic, of what traffic is allowed between what SGT tags back and forward. And the SGT rules are downloaded by supported layer 3 switches. So security group access list It means that you go on ICE, you define like an access list of SGT tags. What SGT tag can speak with what other SGT tag. And then switches, layer 2 switches are going to download that ACL, but based on SGT tag values from ICE. And using that ACL from ICE, they're going to control IP traffic back and forth to the SGT values. So looking at that Cisco document, we should have also something in here like that. Let me look for SGACL. And let's look for a diagram. Hopefully they have one in here. Probably it was a bit upstream. Well, what I can do is let me go to the one of the main diagrams in here. I'm going to show you. I'm going to join there. It's going to be faster this way. Okay, so let's take a look at this diagram in here. Let's assume the following. Let's assume that this user got assigned an SGT value of 10, and this user got assigned an SGT value of 20. And then, of course, then those values have been assigned to those users by Cisco ICE. Let's say this is going to be our ICE server in here. And actually, let's put ICE to be not that device, but let's say ICE is going to be this device. This is going to be my ICE server. And in the data center, we have this server PCI, which is going to have a static SGT value of 90. And this HR server with an SGT value of 50, let's say. Now what do? You go on ICE in here, and you configure that access list, the SGACL, based on tags, which you're going to say something like a tag of 10 can only speak with a tag of 90, and a tag of 20 can only speak with a tag of 50. Let's say this is our basic policy on Cisco ICE. What happens is that this layer 3 switch is going to download from ICE this list, this access list, and all traffic flowing through, if it's of course tagged with SGT values, is going to get controlled by this access list. So this is the point of enforcement where SGACL is being enforced. So what this means is that if this user wants to send traffic to this server, it is going to be allowed because it goes 10 to 90, and that's allowed per my policy from ICE. So the enforcer is going to allow that traffic to flow through. But if this user with a tag of 10 wants to speak with the HR server tag of 50, so as traffic flows to the network, the tag of 10 is being preserved for that user, hop by hop, tag of 10, tag of 10. But now when the enforcer, the layer 3 switch, receives that packet with a tag of 10, but it's destined to an IP which has an assign tag of 50, because the policies that that switch has downloaded from ICE doesn't allow traffic to flow 10 to 50, only 10 to 90 and 20 to 50, it means that the layer 3 switch is going to drop this packet as expected. So it's simple. We came up with this technology so that we scale the firewall rules, and we make the firewalls to be context aware, not IP based, because based on the context, the user is going to get assigned another tag, and then we go on ICE. So we assign the tags. We then all devices in the transport in the transit are going to preserve the tag, and then at some point in the network, we're going to have the layer 3 switch, which downloads the firewall rules based on SGT values from ICE, and all traffic flowing back and forth is going to be controlled based on those rules. The second type of enforcement can be done via SG firewall, which means in this case, the SGT rules are not configured centralized on ICE, but independently and locally, for example, on Cisco ASA. So the firewalls have to be, SG firewall means that the enforcer now is going to be a firewall, not a layer 2 switch. And a firewall can be either the ASA firewall or the iOS zone-based policy firewall. But in both cases, it means you define the rules locally in there. You cannot download the rules from ICE, as in the case of security group access lists. Now, look on MACsec. So as we said, MACsec offers hub-by-hub connectionless data confidentiality and integrity, like an IPsec tunnel or SSL tunnel, from the protection point of view. But there is no tunneling of data, just protection, because we're going to encapsulate everything which is above layer 2, because MACsec is MAC security, so only the layer 2 header is going to be visible in clear text, and it's hub by hub. And it's line rate low latency encryption, so we can have 1 gig, 10 gig, 40 gig, 100 gig, whatever Ethernet is going to become in future, going to be able to provide line rate encryption of also 100 gig in there. Now, MACsec has its own applications on both WAN and LAN. Of course, the challenge being that on both WAN and LAN, clear text traffic may be intercepted. And the problem with the IPsec tunnels is that transit devices cannot inspect the payload. And also, IPsec encryption is very expensive and lacks throughput. So that you're not going to find nowadays, it's very expensive to buy an IPsec device, a device which performs IPsec encryption 100 gig. And also it has latency. While MACsec, it was designed because it's going to be a hardware accelerated feature, it's layer 2, it was designed so that it's line rate, low latency, and cheap. So if you look in here at one of the presentations for Cisco Live Berlin 2016 for MACsec, an introduction section. So they state about network security today for LAN. So if we would build an IPsec tunnel between this user and this user on the LAN side, then transit devices see nothing at all, because it's an IPsec tunnel. And nowadays, we would want actually visibility on the traffic in there so we can inspect it. Because you can imagine that with this setup in here, the network is blind. We don't know what those users are sending back and forward. We cannot do any application layer inspections in there. So MACsec, it adds hub-by-hub encryption. So what happens is that, for example, as a traffic is going to flow from this user to this destination in the data center, traffic is encrypted hub by hub. So between the user and the access point is going to be encrypted via specific wireless encryption. MACsec is of course only wired, not wireless. So on the Wi-Fi side, it's a regular Wi-Fi encryption. But then on the, so I haven't chosen the proper example. To keep it simple, let's think about the connection between this wired users and this data center resource. So what's going to happen is that traffic is going to be encrypted hub by hub. So the traffic exiting that device is going to be encrypted till the next stop, which is the layer 3 switch. The layer 3 switch decrypts the packet, does any kind of inspections, routes the packets further to the other switch, and it encrypts the packet as well. The other switch decrypts it, performs inspections, routes the packet further, encrypts it again, and so on. So packet is encrypted and decrypted hop by hop. So the advantage of MACsec is that not only is cheap, low latency and line rate, but it also allows the network to do application layer inspection because traffic is encrypted and decrypted hop by hop. This is just a fundamental, let's say, overview of MACsec, of course. And of course, in the end, as I stated before, as we started this presentation, ICE is aimed to protect against the full attack continuum, which means before the attack had happened, during the attack is happening, and after the attack had happened. You have that presentation of Cisco in there, where what they state is that, of course, the ICE has evolved from NAC, and Cisco also called it endpoint visualization, access, and security. So you can read about this in there, but what this means is that ICE is able to protect before an attack is going to happen. So on the before phase, because it's going to authenticate and authorize the users based on the health state of the system. So if the system is infected, ICE is going to grant no access to that user. So that's the before phase. Now the during phase and the after phase are, for example, as I said before, is that if an MDM solution identifies that a mobile device got jailbreaked, so it possibly could be infected, then what the MDM is going to do is going to tell ICE, hey, we have this device which is no longer compliant, and at that point ICE is going to instantly change the authorization of that device in the network. So it's going to restrict further network access, so it can contain the attack, so it can remediate that device, clean the device from the infection, and then put it back in the network. So that's why ICE covers all three phases of the attack.